right? So what do you do, right? Clearly, recognizing that it is NP-complete is an important step, right? So otherwise, you'll be banging your head against the wall trying to find an efficient algorithm for an intractable problem. Okay, so certainly the first step is to recognize that the problem that we're dealing with is NP-complete. Okay, but it doesn't stop there. Okay, so once you have proved that it is NP-complete, the next thing to do is to figure out, okay, how do I develop a practical way to solve this problem? Okay, maybe I need to spend a lot of time, and my algorithm is going to be slow, but still there is a difference between an algorithm that takes 4 hours and an algorithm that takes 4 years. Right? So we need to figure out, is there a way I can make my algorithm work in 4 hours and not 4 years? Right? So that's what we're going to talk about. Okay? Of course, even before you go to that step, you need to ask yourself, okay, do I really need to solve this NP-complete problem, or can I change the problem in some way? Okay? Can I simplify the problem in some way? Can I restrict the problem in some way, right? And by doing that, if I'm able to, you may be able to find an efficient algorithm, right? Once again, that step should precede the step 2b, where you're trying to find an efficient algorithm for, not efficient algorithm, but you're trying to find how well you can do, right? So given that it is NP-complete, how far you can go in terms of developing something that is usable in practice. So in this chapter, we are not going to talk too much about step 2a, right? So that's something that you need to always think about, because formulating a problem is the biggest step in solving a problem, right? So it's not, if somebody gives you an abstract problem, right, then finding a solution to it is often easy enough, because there is enough knowledge out there. You can look at books, you can look at Wikipedia, wherever, right, and then you'll be able to eventually solve it without spending too much time. Most of the times, the real problem is formulating, right? So how do you formulate the problem in such a way that it abstracts out unnecessary details, but still captures essential structure that might help you come up with a good algorithm. Okay, so that's certainly a big part of this problem, and that's not something that we are trying to sort of do in this class, right? In this class, we are trying to say, okay, suppose you can abstract and come up with an abstract formulation. How do we go from there to solve the problem? Okay. So again, this chapter, what we're going to do is we're going to say, you have to solve this intractable problem. How far can you go in terms of coming up with something that you can live with? Okay. So a typical approach for solving a search problem, right, is exhaustive search, right? So almost any problem you can think of, if you search for sufficient amount of time, and if you search exhaustively, you can solve the problem, right? So let's take our favorite example, Hamiltonian tour. So the way you can convert it into an exhaustive search is you start with an edge E, and then you say, well, either this edge is part of this tour, right, part of the Hamiltonian tour that I'm trying to construct, or it's not part of the tour. Okay. So now what I'm going to do is I'm going to first consider the case that this edge is part of the tour. Okay. So then once I say it's part of the tour, then what do I do? So I have this graph, right? And I have this edge E, right? So I want to try the two possibilities. Case 1 where E belongs to this tour, and case 2, E does not belong to this tour, right? So if I consider E to belong to this tour, then I have to find a path that goes from this side of E to that side of E while visiting, all the vertices except these two, right? Okay, so I do that search, and if I come up with a path, right? If I find this path, then I'm done, and I have completed. I found a Hamiltonian tool. If not, then I'm going to say, well, maybe E is not part of this tool, so I'm going to, take out E, right? I'm going to just delete. Let me use this notation. So I'm going to just delete E from this graph, because now that I've explored all possibilities involving tools that have this edge E in it, right? And I have come out empty, so now I know, okay, so E does not belong to any Hamiltonian tool. So I might as well just delete it and look for a tool that in a graph that does not even include this edge. Okay, so this is how I'm going to do this systematically. And then let me try to write down a recurrence that corresponds to this algorithm, right? So we have two cases, right? Case one is that E is part of this tour, okay? And once again, I am left with a subproblem that finds a path in a graph that does not contain E, right? Or E itself is not in the tour, so I just delete it and rerun the problem on a graph of some size one less than before. So that's why we end up with this, right? So we end up with this kind of recurrence, which says that you reduce the size of the graph by 1, and you have two such instances of the problem, right? One that looks for paths in which that include E, and one that looks for paths in which E is not included. Okay, so M here is the size of the graph. Okay, so we end up with the problem that says, okay, T of M equals 2Tm minus 1, and so you can very easily see that that is essentially an exponential algorithm which has which works in order of 2 power m. Okay, so very easy to do this, right? So similarly, if you have a SAT problem, then once again you can try every possible truth assignment, and there are only 2 to the power n, right? Because there are n variables, right? Then you have 2 to the power n possible truth assignments, right? Because each variable has 2 possible truth assignments. So if n variables have 2 to the power n possible truth assignments, so you try them systematically, then you are going to have the problem. You're going to have a solution for the problem. Okay. But of course, exhaustive. If you're just exhaustive, do a search exhaustively, then you're probably not doing as well as you could, right? Because the term exhaustive already suggests to you that perhaps you're not being very smart. And so what we want to do is to be intelligent in our exhaustive search, so that we will try to avoid searching in subspaces that actually don't contain the solution. Okay, so how do we do that? So the first step is, of course, to be systematic. Okay, so we need to make sure that we don't revisit the same portion of the search space, right? So we want to avoid searching the same subproblem again and again, right? So we want to do, and one way to do this is to use what is called backtracking. Okay, so in the Hamiltonian tool example, what we did was we looked for a path that includes E and does not include E, right? So what we want to do is we want to systematically search down both of these branches. Okay, so this is like a search tree, the root, and the root has 2 children. The first child include solutions, Hamiltonian tours in which E is included, and here are solutions that don't include E in the Hamiltonian tour. Okay, so what we need to do is we want to search through this graph in an intelligent way. Obviously, one of the things that we would like to do is to avoid spending too much storage, right? So exponential amount of storage is something that we generally cannot afford, right? Exponential amount of time, maybe, right? Exponential amount of storage, almost never. So backtracking is a way of doing this using a depth-first approach, okay? So what we want to do is we want to traverse this search tree in a depth-first way, and therefore we will go down this branch and then we'll systematically explore this tree, and then when we come back, then we'll go down that branch, okay? So the backtracking basically means that once you're finished, so at each node you're going to remember various choices that are available to you, and once you have explored some of the choices, you're going to come back and explore to the next choice. Okay, so that's the, you're deep inside here, and then you finish, and then you come back, and then you try the other alternative over here. So that's the backtracking part. Okay, so just backtracking, hopefully, in most cases, can ensure that you're not, looking at the problem again and again, the same sub-problem again and again, but you would like to do even better, okay? And we'll talk about that a little bit later, but meanwhile, let's see how a backtracking approach works for a problem like SAT, okay? So it gives you a flavor of what this search tree looks like for a concrete problem. So let's look at so this is not 3-SAT, okay, this is just general SAT. That's why there are clauses that have, say, 4 literals here, right? So it's not 3-SAT. So some of the clauses have 2 literals, some of them have 4. So now what you're going to do here is to try, you're going to pick a variable, and then you're going to try the 2 truth assignments for the variable, okay? So at the root, let's say, for whatever reason, we chose W, okay? So the left branch explores the set of solutions where W is equal to 0, and the right branch is going to explore a set of solutions where W equals 1, okay? So once you set W equal to 0, then you can simplify the clauses that have W, right? Because you can basically say, okay, I can just delete W from there. So this clause W or X or Y or Z becomes X or Y or Z because W is false, right? Similarly, W or X bar becomes X bar, X or Y bar becomes X, there's no W, so it just appears as it is, and Y or Z bar once again appears as it is, and then the Z or W bar, right? So W is false, therefore W bar is true. So Z or W bar is going to be true, so that clause is already satisfied, so you no longer have to carry it around. So you drop it the same way. So essentially what you're going to do is, out here, you're going to drop any clause that already has a W bar in it, okay? And then you're going to, from every other clause, you're going to just delete W, okay? So as a result, you are left with a subproblem which is smaller than the problem that you started out with, okay? But while it is smaller, it's basically the same problem. So you can recursively apply the same strategy. So you pick another variable, in this case, let's say we pick X, and then we set X equal to 0 and X equal to 1. If you set X equal to 1, then you will see that there is this clause, X bar, that's going to become false, right? So now once it becomes false, obviously that means it's not satisfiable, right? There's one clause that's false, well, it's not satisfiable. So the way we indicate false is by using an empty clause, right? Because remember, this is CNF, which means that each clause, there must be at least one variable that evaluates to true, right? And if that clause is empty, well, there cannot be one variable that evaluates to true, right? There's not even there is no variable, right? There's no variable to pick. So an empty clause here means false. So, and of course, false and anything is going to be false. So you're not going to explore that branch further because you have shown that there is no satisfying assignment on this branch. Okay? So you explore x equal to 0, and once again you do the same thing. You eliminate x from this clause, and x bar becomes true, so you eliminate it. And XOR Y bar again becomes Y bar, and Y or Z bar, well, it doesn't have any X, so it just appears as it is. Okay? And then you do that again. Now you pick Y, and then if you set Y equal to 1, once again this Y bar cannot be satisfied, so you get an unsatisfiable case. And then you proceed, and then what you end up seeing here is that all of these, you end up here with Z and Z bar, which is obviously not satisfiable. Now let's go down this branch where W equal to 1, and let's try to set, and when W equal to 1, you end up with already something that has Z and Z bar. Well, obviously Z, once you have Z and Z bar, that can never be satisfied, and so you end up with a solution that, okay, there is no satisfying assignment for this CNF formula, right? So this is how you use backtracking to find a solution for SAT. Okay, and in this case, the solution doesn't exist because the formula is unsatisfiable. Okay, so now so let's try to estimate what is the complexity of this approach. Okay, so how long does it take to solve this problem? So we will talk about two cases. Case 1, where both W and W bar occur in the formula. Okay, so this is, so in here, right, both W and W bar occur, right, which means that I need to go down both branches. Okay, so if only one of them occurs, well then that's case 2. Okay, so if both W and W bar occur, then what we are going to be able to do is, right, we eliminated, so in both branches we eliminated W, right? So we are able to eliminate one of the variables. So instead of having n variables to start with, now the subproblems have n minus 1 variables, right? So that's why we have let's talk in terms of literals. So we have let's talk in terms of literals, right? So both W and W bar are there originally, so there were n literals. Now in both subproblems, W as well as W bar have been eliminated, so you have n minus 2 literals. Okay, so that's why you have T of n equals 2T of n minus 2, right? And the O of n comes from the fact that, well, once to eliminate W and W bar, well, you have to go through the formula and then remove occurrences of W and W bar, right, and simplify that clause, right? So that takes linear amount of time, the linear in the length of the formula. That's how you get O of n. So what we are talking about is, okay, to go from here to these two subproblems, right? So this is T of n, this is T of n minus 2, and this is T of n minus 2 because we eliminated both W and W bar. Okay, so now we have 2T of n minus 2, and then to simplify this, to get to this subproblem from here, we may have to make a linear scan through this and remove W and W bar and so on, and that's how we get this O of n term. Okay, so now let's consider the case where only one of the two literals is present. Okay, in this case, we don't have two branches, right? So we only have a branch where that variable is true or false. So for instance, let's say W bar never occurs. Okay, if W bar never occurs, that means, well, you can set W to true and go from there, right? Because that's not going to make any clause false, right? So the only way setting W to true can make the formula less likely to be satisfiable if W bar occurs somewhere, right? So otherwise, if you make W true, it's not going to make the formula false. So as a result, if you have only W or W bar occurring, you just have to explore the one side of the tree, right? So there is no example of that here, but let's say that out here there's only Z and not Z bar, right? Then you will only explore the path Z equal to 1, and this branch will not be there. Okay, so because in this case you don't have two subproblems, you have only one subproblem. So the formula, the recurrence becomes T of n equals T of n minus 1, right? There's only one subproblem, but also you lose a little bit in the sense that you no longer have, you haven't eliminated two literals, you only eliminated one, because only W or W bar, only one of them occur. Okay, so you have T of n equals T of n minus 1 plus O of n, and it's very easy for you to see that this recurrence by itself is like has a solution which is n squared, right? So this is not going to lead to an exponential factor. It is this that's going to lead to an exponential factor. So you can pretty much ignore case 2 and say the worst case is one that corresponds to case 1 occurring repeatedly, which means that you have a solution which is order of n power n by 2, or order of square root 2 to the power n. Okay, so this is order of square root 2 to the power n. And again, what I'm trying to show you is that even though the problem is NP complete, it doesn't mean that you have 2 to the power n or 2 to the power n power k. You can try, you should do your best to try to reduce this exponential factor as much as possible. Yeah?
The analysis we have done is, in this, the factors will not be same always. Like in your reference, at one level there might be W and W prime, in the next there might be only X. So,
but this is the worst case, right? Because this right, is only going to increase the work by a linear factor, right? So this is not a, okay, so let's try to take this, and there are multiple ways to think about it. So one way to think about it is, let's say, okay, so let's okay. So if this is the one that's going to lead you to 2 to the power n by 2 factor, right? So whereas if you follow the other one, then you end up with which is nothing but n times O of n, right? So these two are, that is exponential factor. So anytime you use this expansion, right? So what happens is that you are able to, have only a linear increase in the amount of work you do. Whereas whenever you have a two-way branch, you have exponential increase. Again, if you imagine a binary tree, right? So if you have binary trees where some nodes have two subtrees and some nodes have one subtree, well, it's obviously the nodes which have two subtrees that are going to make a big difference to the size of the tree, right? The nodes that have one subtree, well, they don't even make any difference really to the size of the subtree. So yeah, there is one thing that I did here which you should sort of note. So what I wanted to do is to illustrate in a simple way that you can, by a tighter analysis, you can come up with an algorithm that seems to improve over the original exponential time algorithm, right? But we need to be careful about what is n that we are using, right? So when we said you can have 2 to the power n solution by trying every possible value for each variable, right? There n was the number of variables, okay? Whereas here I'm using n as the number of literals. So what I have done is essentially, well, obviously the number of literals is twice the number of variables. So even though I have given you 2 to the power n by 2 solution, well, if n was actually a number of variables, all I have is 2 to the power n, right? So you should remember that I haven't really achieved any improvement here, but there are lots of algorithms for SAT which do achieve, a complexity less than 2 to the power n, where n is the number of variables. Okay, but it's just that I don't want to go into that now because those algorithms get to be more complex. Okay, and I believe that the best known algorithms are, something like O of 2 to the power, O of 1.2 to the power n. I believe these are the best known satisfiability algorithms out there, and there is no reason to believe it cannot be improved. But as you know, with some of the algorithms we have discussed in the past, as you decrease the exponent, the algorithm becomes more and more complex. The constant factors increase, and so at some point, it's not very clear whether you are really gaining a whole lot or not. Okay, so we want algorithms that are systematic, but it doesn't mean that we don't like to use heuristics at all. So one heuristic we could use is to say, well, let me pick a variable that occurs many times. Okay, so if I pick a variable that occurs many times, and let's say I count the number of the size of the formula as n, okay, then by picking a variable that occurs many times, then I will achieve, if the variable occurs k times, then I will achieve, I will be left with a subproblem which is order of n minus k. So clearly that seems to achieve more of a reduction in problem size than using a variable that occurs fewer times. But you're not going to always find these variables, because if you can do this repeatedly very fast, then you will be able to achieve an algorithm that's much faster. But no, that's not going to work, and so it's not going to make a lot of difference to the worst case complexity, but that doesn't mean that you should try to use these heuristics to improve your algorithm whenever you can. Okay. So that's pure backtracking. Okay. Now the thing about backtracking is we are simply doing exhaustive search, right? And then we are trying to see, okay, in the exhaustive search, the next thing that we want to do is try to do the search in an intelligent fashion and in a way that avoids searching through subspaces of your problem space where there are good solutions. Okay? So branch and bound is a class of algorithms where you are working with some sort of a bound on the how good the solution is, and then if whenever you go to a part of the search tree where good enough solutions don't exist, you're not going to spend time searching that subspace anymore. Okay? So in order to do that, you need a bound. You need to say, okay, the least cost solution in this subtree is going to have at least this much cost, and if I already have a solution that's better, then I won't go into that. Okay? So the way I'm describing this, it's already clear to you that this is not for a decision problem. It's for a problem where I want an optimal solution, right? So it's for an optimization problem, not a decision problem, right? Again, SAT is a decision problem where we are trying to say, does there exist a satisfying truth assignment or not, right? And whole of NP completeness is built, or the whole of the complexity hierarchy is built on decision problems. Okay? But we've already talked about how optimization problems can be thought of as formulated as a decision problem by providing a bound and saying, okay, do you have a solution whose bound is better than X? Okay? So now, once you have that bound, then you can use this information to prune out search spaces, subspaces that are not going to yield a solution. Okay? So, or if you're not interested in the decision problem, you're only interested in the optimization problem. Let's say one part of the search tree has already yielded you a solution that has a cost of 10, and on this subtree, your minimum cost, you can bound it to be 12. Well, there's no point exploring this subtree because you already have a solution that has cost of 10. Okay, so let's take our traveling salesman problem and try to illustrate the branch and bound technique for this problem. Okay, so the way we are going to do this is, well, how do you find a solution to TSP? Well, you start with some vertex and then you gradually build up a path going through every vertex in the graph, ultimately ending back at the same vertex. Okay, so let's say we pick a starting vertex A, right? So in this case, it doesn't really matter, right? Where we start doesn't matter, right? Because everything has to start at some point and it's a cycle. So it doesn't matter where you start and end. So let's begin with the vertex A. Okay, so we are trying to compute a TSP that begins at A and ends at A. So, well, this tour should start with some edge from A, right? So we pick an edge, right? And then using that edge, we go to its neighbor X, and then from X, pick another neighbor, and then from there another neighbor, and so on, and we keep doing this until we complete the tour. Okay? So, now, in order to understand branch and bound, we need to understand, okay, how do I derive this bound on cost of solutions that I can find in a part of the search space. Okay, so I need to do this. How do I do this? So for that, I need to think about what is a solution and what is a partial solution. What does it mean to complete a partial solution? Okay, so let's say so far I have sketched out a path from A to B. So I have this graph. I started from A, right? And I have reached vertex B. Okay? And so what I need to do is I need to complete this path, right? So I need to find this part of the path, right? So this is done and this is to be done. Okay? So the partial solution represents that I have found so far is this path. Right? So this is the partial solution. This partial solution includes a bunch of vertices. Okay? So let's call this includes S, which is a subset, but we can say it's a proper subset because if it's the entire set V, then we are done, right? So it's going to be a partial, it's a partial solution because S is a proper subset of V. Okay. Now, by the nature of a TSP, this path that you need to find in order to complete this must not include any of these vertices S, right? So S is already covered. What you need to cover is V minus, so TBD, right, to be done, part covers vertices V minus S, right? So everything that's not covered here has to be covered here, right? So that's the nature of, completing the partial solution means we need to find a path that goes through every vertex. So how do we find a bound on this, the part? So what we want to do is we want to do essentially our search tree, we want to do our backtracking, except that at every node we want to have an idea of what is the best solution we can find below this node. Okay? So for that we need to essentially find a lower bound on the cost of this part, which is denoted as TBD. Okay? So how do we come up with a bound? So we have this path, right? So from A to B. So we need an edge that goes from A back into this part, right? And we need an edge from B going back into this part. And then we need a path that connects up everything else, right? So those are the three components. And then we can do a bound on each of them. Okay? So the bound on the cost of this edge is easy to find, right? So we basically take all of the edges that go from A into this part, right, which is V minus S, right? We consider all edges that go from A to this part of the graph, okay, and we pick the minimum cost edge, right? So obviously you have to use some edge, and the lowest cost edge, if you pick, that should give you a lower bound. Same way, you look at all the edges from B that go into this part. And once again, you pick the minimum cost, and that's going to give you a lower bound. Now we need to figure out, okay, let's say this is X, and let's say this is Y. We need to figure out what is the minimum, what is the bound, what is the lower bound on going from X to Y. Okay? So what we are going to say is that the lower bound on this is that there cannot be a path that is less expensive than the minimum spanning tree. Right? Why is that? I'm saying that the cost of this path, okay, so this is the part that includes S, this is the part that includes V minus S. Okay? So what I'm saying is that the cost of this path, right, cost of X to Y is greater than or equal to the cost of MST for V minus S. And the reason is actually very simple, right? Suppose I have a path that goes through every vertex in V minus S. Okay? Well, by definition, that is a spanning tree, right? A path that goes through every vertex is by definition a spanning tree, right? So you obviously cannot have a path like that whose cost is less than minimal spanning tree, because minimal spanning tree is the spanning tree with the minimal cost. So as a result, this path that goes through every vertex in V minus S cannot have a cost that's less than the cost of the minimal spanning tree. Okay, so thus we have a bound on this part, and this part. So we can say that this whole part of the TSP that we are going to find, or the to complete the solution, our cost is going to be greater than or equal to the cost of the least cost edge out of A plus least cost edge out of B plus the MST for the part of the graph that we haven't covered yet. Okay, so we're going to use those three, and then we're going to use that as the bound. So here's an example. So here is your graph, and we're going to use this branch and bound. We're going to illustrate the construction of illustrate the branch and bound algorithm using this particular graph. Okay, so let's see. So what we are doing here is we are starting from vertex A, right? So vertex A in the graph, and let's say we pick the edge going from A to B. Okay, so we pick this edge. So we have A, and we're going to B. Okay, so now if you go to B, then we have picked this edge A to B, right, which has a cost of 2, right? So we have cost of 2 already, right? So now let's try to complete this picture, right? So now in this picture we have A and B and cost 2, right? This is what is the partial solution we have computed so far, right? So that's what corresponds to, what is done. Now we want to find the least cost edge out of A into the rest of the graph, and the least cost edge out of B into the rest of the graph. And you can see from here, the least cost edge out of A has a cost of 1, right? So so we have a way of going out of A and B. Now we need to visit every vertex, right? And every other vertex in the graph. And as we said, the bound on the cost of this path is the bound on the minimal spanning tree for the graph, right? For the graph after deleting A and B, right? Because so we have A and B already, we have covered. Our V minus S includes every vertex except A and B. And what we want to do is we want to figure out what is the minimal spanning tree for that, and that will give us this bound, right? So let's try to draw the minimal spanning tree over here. Okay, so we have H, C, G, D, F, E. Right? So these are the vertices that are left, right? These are the V minus S vertices, and we want to construct a minimal spanning tree for this, right? So how do we do this? Well, we pick the minimal cost edge and keep adding as long as we are not creating cycles. So obviously we'll pick G to D, which has a cost of 1, G to H, which has cost of 1, and let's see what else do we have. D to C, which has cost of 1, and then we can pick either G to F. Well, we'll pick F to E, which is 1, right? So now we have to pick just one more edge, and we have only choices we have left. Lowest cost that's left at this point is something like that, right? So what is the cost of the spanning tree? $6, right? So what is the cost of this? What is the bound on this solution? 10, right? So that's what you see over there, right? So next to B, you have calculated this bound and said, okay, the best solution I can find below this node is going to be 10. Okay? Any questions? So let's do this for one more case. Let's say we look at going down from A to F. Okay? So if you do A to F, okay? So let's say our first choice that we pick is right? So if you go from A to F, that is the second branch, right? So again, we are systematically trying every edge out of A, right? So we start with A, we try every edge, right? The first edge we try is the one that goes from A to B. The second edge we are trying, you see that there are only 3 edges, right, for A. So we're going to try A to B, A to F, and A to H, okay? So we tried A to B, we ended up with 10, and I'm not going to go through the rest of the tree because obviously it will take me 3 lectures to finish this whole tree. So we just explored some parts. So let's go from A to F. So we have cost of 1, okay? And then again, the same routine, right? So we want to find a bound on the minimum size spanning tree we can get. Minimum cost TSP that we can get starting from this edge, okay? So once again, we need to find the least cost edge out of F, least cost edge out of A, right? So the least cost edge out of F is again 1, least cost edge out of A is again 1, right? So, okay, and then we need to find this path, which again, we know the bound on that is the cost of the minimal spanning tree for the rest of the graph while when you leave out A and F, right? So let's construct that. Right, in this case, A and F have been left out. So we start with this, and you will see once again that I will add those edges, and then what else do I add? So B to C I can add, right? And what else do I have?
E to B.
B to E, right? So that's 1, right? So in this case, I have a spanning tree which has a cost of 5, correct? So the lower bound that I have on this path length is 5. So the lower bound on the cost of the solution that includes A and F is 8, right? And that's again what you see associated with the vertex called F. Okay? So by systematically exploring, you can find all the solutions, and what you're going to do is you're going to avoid exploring paths where you have a lower cost solution. So for instance, in this particular case, you have the way the search tree is drawn is you are first going to look at B, and then you're going to go depth first into B before you come here, okay? And what you're going to do is the moment you have computed an actual solution that has a cost of 11, right? Then you are going to avoid exploring any subtree where the lower bound on the cost is more than 11. You understand? Right? The fact that you have a lower bound 10 here, okay, doesn't mean that you're going to find a solution that has a cost of 10. It just means that you cannot find a solution which is less than 10. That's all you know. So what a branch and bound algorithm has to do is it has to find the first solution. right? Only after finding the first solution, it can actually start pruning away some parts of the search space. Because once you have a solution that has a cost of 11, you no longer explore these costs, right? So for instance, okay, so you have 11, well, why bother, going into branches where the minimum cost is at least, 14, right? You already have 11. You could also use another heuristic which says, okay, I'm not going to go into B first, I'm going to go into F first because F seems more likely to produce a lower cost solution, right? Of course, I don't know that it's going to produce a lower cost because it's just a lower bound, right? But it stands to reason that there is a better chance for finding a lower cost solution, so I might actually go down this branch first, and if I did that, then I would have not explored any of this, right? So if I did that, then all I would have done is, well, I will just, if I use that heuristic, you can see that I'll pick this, then among the two children I'm going to pick E, and again among the two children I'm going to pick B, and then B has only one child, C, and once again I'm going to pick the low cost. So you can see that if I use the heuristic in a deterministic fashion, in almost deterministic fashion, I'll just get to the optimal solution without really an exhaustive search. So that's the advantage of a branch and bound. It allows you to eliminate parts of the search space without having to explore all of it. Okay? And the key point in order to do a branch and bound algorithm, what you need to be able to find lower bounds on partial solutions. Okay? Or lower bounds on solutions that could result from the partial solution that you have. Okay? So once you do that, then you can have a branch and bound algorithm. So let's stop here. I want to take the